So in the previous class, we have derived the equation for the calculation of stresses for the curved beams. In this one, we are going to apply this equation to calculate the stresses at different locations in a curved beam. So the question is that we have been provided with a curved beam, something like this one, on which there are movement of 4 kilonewton per meter. 4 kilonewton meter is acting on the cross section, and we are supposed to figure out the maximum normal stresses. These distances or radius are given, so we know that the formula for the curved beam is dependent on the movements and the radial distances, so it would be quite simple. So we have this formula for the stresses, that is m over a into capital R minus, sorry, it would be R bar minus capital R into 1 minus capital R over small r. Now if we want to calculate the stresses at any cross section, let's say in this one, we will consider this cross section. Okay, so this R distance is the distance from this center of curvature to these particular points. For example, if I want to calculate the stress at this point B, this R distance would be 200 millimeter. And similarly, if I want to calculate the stress at this point A, then this R distance would be what? 280 millimeter. Right? So this R distance is a variable. If you want to calculate the stresses at different points, we have the different distances. This capital R, if you remember, is the distance of neutral axis, and we have one relationship for the determination of capital R. We will use that. And this area is the area of the cross section. Now this is the cross section of this curved beam. It has a rectangular shape on top. For example, if you see these lines or these markings, so it has a rectangular shape, or it's a combination of a rectangle and a triangle. So this is the cross section, and this A factor is the area of cross section. This R is the centroidal distance, or the distance from center of curvature to the centroid of this body. And this capital R is again neutral axis distance. So if we can figure out these factors, we can calculate the stresses at any points. We have been provided with this movement that is 4 kilonewton meter. So first let's see how we can calculate this R dash or R bar. So can anyone tell me that what is the relationship for the calculation of centroidal distance of any cross section?
So integral of R over area.
X dA divided by dA point.
So we have this shape, right? And this is 50 millimeter. So either it should be integral, or we can take it as summation. This is also 50 millimeter. This distance, this height is 30 millimeter, right? So this R, or the centroid of any shape with respect to any particular point, is summation of R bar A, or R bar A factor for each of these shapes separately divided by total area of this cross section. So first let's calculate the total area. So what will be the area? That will be 50 into 50, or we can convert it into meter units, because everything would be in meters later on. So that will be 0.05 square plus half this triangular area. That will be 0.03 into 0.05. So what will be this area? The total area of this cross section. Anyone? Are you using calculators? Class, can you give me this area?
3.25 into 10 to the power minus 3.
So it is 0.00325. And in this calculation, one thing that I forgot to mention is that you should try to consider at least up to 5 significant digits, because these r dash factors, this r and these small r, they all are radius and they are primary factors which are governing the stresses. So try to be as much precise as you can, because if you consider less number of significant figure, then these stresses can vary significantly. So at least go up till 5 significant digits in the answers. So this area is this factor. And now if I want to calculate this factor on the top with respect to the center of curvature for this triangle, let's call it as 1 and this as 2. So what will be r bar into a? So what will be this r bar factor for this triangular shape with respect to center of curvature? What will be this distance? This r bar distance for this rectangular shape. It will be the distance from the center
250.
to the center of this body. So this distance is 200. So up till center it will be 250. So if I represent it in 250 or 225, yes, it should be 225.
225.
So this distance is 0.225 and area for rectangle is again 0.05 square plus for this triangular shape, what would be the distance? 250 plus this distance to the centroid of this shape. What will be this distance? 1 by 3 into 30, right? It will be 10. So we have 250 plus 10, that is 260. So if I convert it into meters, I will get 0.260. And again, the area for the triangle is half into 0.03 into 0.05. And the total area we have already calculated, that is 0.00325. So what will be this R bar now? Anyone?
0.
0.179.
0.
Is it?
0.233.
Yes.
0.2330.
So this is R bar. Now we have one factor. This R bar we have computed, right? So this is done. So second thing is we need to figure out the location of neutral axis. For the location of neutral axis, if you remember, we have just derived one relationship, that is capital R is equal to summation A over summation integral of A dA over R. Now for this dA over R factor, I have told you before that we will use for rectangular shape, it's convenient to figure that out, but for the triangular shape or other shapes, we can't get it directly. So we will use these tables. In this table, actually, the formula is for rectangle is missing, triangle is missing, so I would write it down over here. That this factor or this integral dA over R for the rectangular shape is this factor. So I will write it down over here. It is, if this distance is B and the distance from the center is R1 and this distance is R2, then the formula for triangle is B into R2 over R2 minus R1 log natural R2 over R1 minus B. So this is the relationship for the integral for the triangular shape. And for the rectangular shape, we already know that the formula is b log natural r2 over r1. So we will divide this section or our cross section into two areas and calculate this integral separately and then just add them. So for the first shape, we have this rectangle that is 50 millimeter and the width is also 50 millimeter. And if this is the center of curvature, what will be R1 distance? If I look into this figure again, this R1 distance from the center of curvature to the top of the shape, that is 200 millimeter. And R2 distance will be the distance from center of curvature to the bottom of the shape. That will be 200 into 50, so it will be 250 millimeter. So for rectangle, R1 and R2 are now known. So this is R1, 200 millimeter, and this distance is R2, that is 250 millimeter. So the integral will be a dA over R is equal to b log natural R2 over R1. So width is 50, log natural R2 is 250, or in meters unit, let's substitute this in meters as well. 0.050, R2 is 0.250 over R1 is 0.2. So what will be this integral for rectangular shape?
Zero point zero one 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 five.
0.011157, and the units are meter. So this is the integral for the rectangular shape. Now let's do the same procedure for the triangle. For the triangular shape, the shape is this one, and if this is the center of curvature, we know this distance is 250 millimeter, and this height is 30, and R2 will be 280 millimeters. So the integral is, or the formula is b into R2 divided by R2 minus R1 log natural R2 over R1 minus b. So if I substitute all these values, I will get 0.030 into R2 is 280, 0.280. So again 0.280 minus 0.250 log natural 0.280 divided by 0.250 minus again the width, that is, actually width is not 0. Yes, it is 0.050. So the width is again 0. So what will be this integral? That is 50.
Two point 86 into 10 to the power minus 3.
Then yeah, so it will be 0.0028867. Okay, so this is the integral for the rectangular shape. Now in this equation for the location of neutral axis, we know this total area sigma.
सर आपकी आवाज नहीं आ रही.
Now can you hear me?
Yes sir.
So for we know this total area, that is 0.325 or something, which we have already calculated, and now we know these two factors as well. So we will sum them and get the location of neutral axis. So the area was 3.25 into 10 raised to power minus 3 or 0.00325. So, and this factor for shape 1 was 0.011157, and for shape 2 it was 0.0028867. So this R factor, what will be this R, or what will be this location of neutral axis? So it will be 0.23142 meters. So this is the location of neutral axis. Now we have all the factors that we needed to calculate the stresses, this distances. So now let's take the cross section at this point AB to get the maximum and minimum values of stresses.
सर ये न्यूट्रल एक्सिस का डिस्टेंस विद रिस्पेक्ट टू क्या है 0.23
With respect to this center of curvature. So it will be something
okay.
over here. So let's take this cross section and calculate the stresses. So this is the cross section, this is point A, this is point B. So we were supposed to calculate the maximum stresses, so we will calculate at two extreme points and we will see that which one is the maximum. So the distance of this point A with respect to centroid is, I guess it is 0.2. Let's see from the figure. So the distance of point, or this is point B, let's call this as point B. So the distance is what, 200 millimeter, and for point A the distance is 280 millimeters. So this is point B and this is point A. So this distance is R for point B is 200 millimeter, and the distance R for point A is 280 millimeter. So let us calculate the stresses. For point B, we have the equation as M A R bar minus capital R into 1 minus R over. Okay, I have one question. Can you tell me that what would be stresses at point B, or either the point B is in tension or will it be in compression? Can anyone answer this? If someone can answer, he will get an extra credit.
पॉइंट बी पे सर कंप्रेशन होगी और ए पे टेंशन होगी.
How come?
सर वो मूवमेंट जो है वो इस तरह लग रहे हैं तो वहाँ पे
So the resistive movement will be this one, right? So at
Yes.
point B, it will be causing the compression.
Compression.
Who are you, by the way? I couldn't.
शाहज़ेब.
Okay. So this is 4 kilonewton meter. So the moment is 4 kilo. Let's see. The area that we calculated was 3.25 into 10 is to power minus 3, and this R distance that we have calculated was 0.23308. This capital R is 0.23142, and this factor is 1 minus, what was capital R again, 0.23142 divided by this small r, or the distance of this point B is 200 or 0.200 millimeter. So what will be sigma B?
Sir, minus 116478.2.
Minus
116478.2.
minus 1164.2.
78.2.
Okay. So the units are kilonewton per meter. So if you want to convert it into Newton per millimeter, or if you want to convert it into megapascal, what will you do? I think maybe there is some mistake in this calculation. Okay, let's try. Kilonewton per meter square, because it is stress unit. So to convert it into Newton per millimeter square, we'll have to multiply it with 1000 and divide it by 1000 square. So what will be the answer in megapascal now? That will be sigma B is equal to minus 116.5 megapascal. So this is your stress at point B. Now from this equation you can see that whenever you get the negative answer, that means the stresses at that particular points are compressive. And from the movement you can also visualize that these stresses are acting in compression at point B. So let's apply the same formula and calculate the stress at point A. So the only difference is the whole equation will remain same, but at this point we will have 0.280. So what will be the stress at point A?
सर आपने अभी ये मीटर्स को मिलीमीटर में कन्वर्ट किया है?
I have converted into newtons per millimeter square.
Sir, 128.6 megapascal.
So you can see that your answer for stress at point A is 128 something megapascal. So it is in positive units, so that means that whenever this equation gives you the positive answer, that section is in compression tension. So if I show the stress distribution at this point, obviously we know that it is non-linear. So when you calculate at different point, for example at this point, you will automatically get this non-linear shape. So the final shape, in this question it was required to report the maximum stress. So the maximum stress is this 128 megapascal. So this is our primary objective. So if you want to represent this on the cross section, it will be something like this one. At point B, the stress is 116. At point A, the stress is 128 megapascal. So if you remember that in the case of straight beams or in the case of rectangular cross section, we have the stresses that are linear. But from here, you can see that these stresses are non-linear for curved beam. So this is it from the calculation or the example. And mostly you are going to get similar kind of numericals in the case of curved beams. So a bit tricky thing is the calculation of this derivative, but you have direct formulations for this, the calculation of this integral, but now you have the direct formulations and you are going to get the shapes for which you know this integral, because otherwise it would get very complicated. And if you have any question about this numerical, you can ask me now. So if there isn't any question, then this is it from our MOS course. This was the last lecture and we have completed every topic. After midterm, if I summarize, we studied the unsymmetrical bending, the cylinders, thick and thin, columns or eccentric columns basically. And the final topic was this curved beams, but there is another topic also, that was theories of failure, for which I have already provided you with the recorded videos from which you can understand that what these theories of failure. And before midterm, our primary topics were stresses and strains. And in this, there were different types by using equation, by using MOS circle, by using strain results. So there were different topics. So this is it from our MOS course. And now you have enough time to prepare before